Hi everyone. In this video, we're going to look at an introduction to rational functions. We'll look at just a couple of simple ones. We'll look at more complicated ones in class. But a rational function is anyone that's in the form of a polynomial divided by another polynomial. And the denominator polynomial can't equal 0 because we cannot divide by 0. So this is going to cause some restrictions in our domain, some non-permissible values of x. So let's start with a very, very basic rational function. F of x equals 1 over x. Now, we don't normally think of 1 or x as polynomials, but they are. They're both monomials. 1 is a constant monomial, and x is linear. So this does qualify as a rational function. And we can pretty clearly, easily, right from the beginning, say, well, then x can't equal 0. Because I am dividing by x, I cannot divide by 0. X cannot be 0. Or more formally, I can write this domain notation x such that x cannot equal 0, but otherwise, x can be any real number. The range is a little bit trickier, so we're going to actually think about some specific points in order to figure out what the shape of this graph is and hope that that leads us to the range. So we can start just by plugging in some values. If x equals 1, for example, 1 over 1 equals 1, so we have the point 1, 1. If x equals 2, we get 1 over 2, 1 over 3. If x equals 3, 1 over 4, 1 over 5. So I can start to see what's happening here as x gets bigger. As x gets bigger, I'm going to get smaller and smaller and smaller fractions. So a notation thing we can do is as x goes to infinity, 1 over x is going to get smaller and smaller. It is going to stay positive because I can't divide 1 by a positive number and end up with something that's negative. And it's never going to be 0 because 1 divided by a number that isn't 0 can't be 0. But it is going to get super close to 0. So I'm going to have 1/10 or 1/1,000,000th or 1/7 trillionth. Numbers that get arbitrarily close to 0. Let's also think of what happens if I have negative values. So if x equals -1, 1 divided by -1 is -1. 1 divided by -2 is -1/2. Divided by -3, I get -1/3. And I can see that a similar thing is going to happen on the left-hand side of this graph. As x goes to -infinity, 1 over x is also going to go towards 0, but this time it's going to come from the negative side because these numbers all have to be negative. I can't have a negative number, or I can't have 1 divided by a negative number suddenly become positive. It's always going to be negative. So this is giving me a hint as to my range here. 1 divided by something can never be 0. So in fact, y cannot be 0. It gets really, really, really close to 0, but it doesn't actually become 0. So these two restrictions, one in the domain and one in the range, are going to help define the shape of my graph. But I want to see what's happening to the graph around 0, because x can be close to 0, it just can't be 0. So let's say x equals 1/2. 1 divided by 1/2 is 2. 1 divided by 1/3 is 3. Divided by 1/4 is going to be 4. 1/5. Okay, so I can start to see again what's happening with this shape. As x gets closer and closer and closer to 0 from the positive side. So in other words, I have numbers that are not 0. Not 0, but close to 0, but they are still positive. Then what's happening is the y value, 1 over x, is going to get bigger and bigger and bigger, and it's going to go to 1,000. So if, for example, x was 1/10,000,000th, then y would be 10 billion. So this is roughly giving me the shape of this graph, and I can sort of see the curve here as the function approaches that restricted value of x and as it approaches the limitation in the range. So these are actually what we call asymptotes. So if I draw a vertical line here where x equals 0, and I draw a horizontal line where y equals 0, these are lines that the graph doesn't reach if I look at the extreme edges. So if I look at what's happening as x gets incredibly large, then y is going to get very, very close to 0. And as x gets very, very close to 0, then y is going to get incredibly large. So these, I'm going to write that word down so that you can see the spelling of it, asymptotes. We have a vertical asymptote at x equals 0 and a horizontal one at y equals 0. So to complete this graph, I'm going to look at what happens for x values that are close to 0, but they're less than 0. So as x approaches 0, but values that are slightly negative. So negative 1/2, for example, I would get negative 2. Negative 1/3, I'd get negative 3. Negative 1/5, I'd get negative 5. So as x goes to 0, but it's still negative, so very, very tiny but slightly negative numbers, 1 over x is going to go towards negative infinity. So the shape of the graph takes on a curve that kind of hugs those asymptotes in both directions, but it never actually reaches them, it just starts to tend towards them. So this shape that we see here, these two branches, it's actually called a hyperbola. These two branches are discontinuous, they're separate. It's not like the other functions we've studied where they're all connected to each other. There is a gap in this function, but these are the shapes that we often see with rational functions. So with that in mind, we're going to look at still a quite simple function, but something that's a little bit more complex than what we just dealt with. And that is f of x equals 2x over x minus 4. Now right away we have a difference because we don't have a constant numerator. We have a variable in the numerator. So in this case, x can equal 0. And in fact, if x were equal to 0, y would also be equal to 0. So any value that's going to make the numerator equal to 0 is going to make the whole fraction equal 0. So that gives us a way to find our x-intercepts right off the bat. So I'm going to go ahead and put that point on the graph. And I can figure out my domain fairly easily as well. X minus 4 is the denominator, so x minus 4 cannot equal 0, which means that x can't equal 4. So that means that I have domain x such that x cannot equal 4, but otherwise x is any real number. So that's our domain. Range is a little trickier, so we're going to think about range the same way we did in the previous question. But first I'm going to go ahead and tell you that x equals 4 is my vertical asymptote. So I'm going to put that on here. There are some cases where a domain restriction is not a vertical asymptote, and we're going to look at those in class. But for this one, x equals 4 is a vertical asymptote. There also will be a horizontal asymptote. So to figure it, we're going to consider what happens as values of x get very large or very, very small. So in other words, as x goes to infinity. Now, as x goes to infinity, so let's say, for example, x equals 10 to the power of, well, let's just go with 10,000 for now. So f at 10,000. 2 times 10,000 is 20,000. That's what I have in the numerator. 10,000 minus 4 is going to be 9,996, which is still very close to 10,000. And actually what we see happening here is that the larger x gets, the more irrelevant that minus 4 becomes. So if I take 20,000 and divide it by 9,996, I get a value that is approximately 2. And in fact, if I were to take even bigger values, f at 10 to the power of 10, for example, I'm going to get values that are approximately 2, because that minus 4 becomes less and less relevant. It's kind of like I just have 2x over x, which is basically 2. And as x goes to negative infinity, I'm going to see something similar happening. So for example, if f at x, if I'm doing f at negative 10,000, I'm going to end up with negative 20,000 divided by negative 10,000 minus 4 is negative 10,004. Again, the higher that value of x is, the less relevant that minus 4 becomes. This is kind of like just dividing 20,000 by 10,000, and we get a number that's pretty close to 2. So that tells me right here that 2 is my horizontal asymptote, because that is the y value that this graph is approaching as x gets larger and larger. It's never going to technically be 2, because I'm never actually dividing 20,000 by 10,000, for example. There is always that minus 4 there. It just becomes very insignificant as x gets bigger. So y equals 2 is my horizontal asymptote. Now, based on what we saw in the previous example, we should expect to see those two same sorts of branches happening here. But I can pick a few points to check it out. So for example, if I pick some values on either side of 4, so let's say f at 3. F at 3, I'm going to get 6 over negative 1, so negative 6. So I've got a point at f at 3, negative 6, so right there. And coupled with 0, 0, I can sort of get the shape here is going to be, that's not really as smooth as it needs to be, but that's basically where the curve is. And if I take a point on the other side, so let's say I'm going to do f at 5 and f at 6. So if I get f at 5, I've got 10 over 1, so 10. So there's a point right about here. And f at 6, I get 12 over 2, so 6. And that's going to go right here. So again, that tells me that I've got a branch kind of in here. Gives me a couple of points to go through and tells me that it needs to be tending towards those asymptotes. So this one has been stretched a little from what the previous one looked like. It's not quite as tight into those asymptotes, but it still does have those 2 branches. So these are some basic rational functions.